All right, this is take one. This is Sarah Braun. Thank you for showing up on the podcast or the documentary or whatever you want to call it. If you could just introduce yourself and tell us a bit more about who you are, maybe your schooling, your career now, and maybe your career at Ridley. That'd be great.
Great. So my name's Sarah. I graduated high school in 2003, and I did an undergraduate degree in math and physics. So I did mainly, my degree was in physics. My specialization was to do a double major math. So then I went into teachers college at Brock, and praise God, God gave me a teaching job right away when no one was getting them at Ridley College, which is a private boarding school here in St. Catharines. And so I taught there for 15 years. I was mainly in mathematics, and I was ahead of math by the end of my career there. And then I quit my job, which I never thought I'd do because I thought I'd retire there at 65 and teach math and physics forever. But I quit my job to become a pastor at New Hope Church. And just before I quit my job there, I had started very slowly working on my master's in theology. So because of how little I'm doing at a time, it's like a 7-year process for me. So I have 1 year left, and then I will also have done my master's in theology. So that's a little bit of my background. But I spent my main bulk of my career teaching math. And at Ridley, we were an international baccalaureate school. So I got the opportunity, which was really fun, to teach a lot of more advanced math courses than the standard Ontario curriculum. So I taught AP, Calc, and a lot of advanced calculus. So like kids would finish my class and then they would skip first year university because we covered all that in high school over grade 11 and 12. So that was probably my favorite to do.
That was your favorite?
Yeah.
Wow.
Okay.
That's cool. Yeah, I was going to ask you what your favorite is, but that's great. I think it's fine here, but
Yeah.
we're going to ask you what your favorite is, but you already said, so
Perfect.
that's awesome. I'm just curious how, you said people come from different backgrounds, different countries, that kind of thing. How did that actually change the way you teach it?
That's a great question. So we had people from 60 different countries.
Yeah.
And so, and they would come, say, in grade 9 or 10 or even in grade 11.
Yeah.
So you'd teach students educated in China.
Yeah.
You teach students educated in Germany and other European countries. And you teach North Americans, a lot of Nigerian students as well who'd gone the British system. So I got to know a lot of different educational systems, which is cool. And as a math teacher, like the biggest thing would be I would see a huge difference in, for example, Chinese or other Asian students, German or other European students who typically are not allowed to use a calculator until very late in their mathematics career. So they their mental math skills are just way stronger.
Wow.
Versus North American students, like American or Canadians, who usually are given a calculator a lot earlier in their instruction. The idea being that you can then get to more advanced level problem solving. But the thing that I would see in students and why I let my own children, like I basically ban them from calculators early on, is because when you actually have to use your working memory to think about what 5 times 6 is, then you're like using up brain power to think about that instead of just like it's 30. Like you don't even think about it, and so you're actually moving on to the higher level problem solving more easily, especially when you have to factor and do some of those other things. It was also interesting to learn, like, say, I taught a lot of native Mandarin speakers, and the way that they say numbers changes how they think about numbers. So like a Mandarin speaker, if they're saying 353, they would say 300s, 5 10s, 3.
Really?
So you never have to teach a Mandarin speaking kid about place value, which is actually a challenging thing to teach an English speaker. They just understand that 353 is 300s, 5 10s, and 3 because it's in the word, right? Another thing that like was really cool was, for example, they don't put a comma after 3 digits. It's after 4.
Oh.
So to say 10,000, like I could have like a student who was way, way better at math than me, the top student in the whole school, and they'd try to be reading the number 40,207 in English, and they can barely do it because they don't say 40,000. You know what I mean? Like what we group as 1,000, that's after 4 zeros. So their 10,000 is our 1,000. So it just was really interesting to see the difference that the language of mathematics affects the thinking of mathematics.
Wow. I never thought about that. That's really cool. So it seems to me like you have like a lot of like a very big math heavy background, and you care a lot very deeply about math and that kind of thing, and understand the natural world through a mathematical lens and that kind of thing.
Especially as a physicist, like that is what I taught math a lot more than I taught physics, but my schooling was a lot more in physics. That was the primary area of my.
And then you also mentioned that you've taught grade 11 and grade 12 chemistry.
Yep, I've taught physics 12. A lot and some chem as well. Yeah.
And so I'm assuming you know a bit about gas laws, like just the simple ones like Boyle's and Charles and Gay-Lussac's laws. And from a mathematical background, maybe you just want to like explain those a bit, like even like how like even like fractions almost play a role into that.
Right.
And even just how those maybe some of those laws briefly just apply to our real world.
For sure. So frankly, I had to remind myself what each of the laws was called, because spoiler alert, that's not really something that sticks in your long-term memory, but this sure does, as I'm sure you guys are familiar with PV equals nRT. And so I think when you get to those different laws, and this is something about like the intuitive understanding of mathematics. So when I did my undergrad, one of the classes I took was actually on teaching mathematics, and it was better than any class I took at Teachers College. But there's some good research that show the point when students decide whether they think they're good at math or not is fractions. If when you're learning fractions, depending on when that is, grade 3, grade 4, whatever, you get it, you're like, math. And those are the people who go on in mathematics and feel good about math. And the kids who struggle with fractions and never get fractions when it's first taught, those tend to be like, that's the parting of the ways in mathematics. So like understanding the difference between how these two laws work is really about, do you understand fractions, right? Like as the temperature increases, if this is going to stay constant, as the temperature increases, well, the volume's also going to increase, because for this value to stay equal to this value, obviously if the denominator gets bigger, the numerator also has to get bigger for this to be constant. But as the pressure increases, for this to stay constant to this, as the pressure increases, well, obviously the volume has to decrease to compensate. So really that's all you need to understand the gas laws. Like when you look at each of the gas laws, you're saying like, for this number to stay stable, because I know the volume over the temperature has to equal the new volume over the new temperature. Well, what has to happen? If the volume increases, for this to stay stable, the temperature is also going to have to increase. And that works the other way in PV equals PV. So put that all together, as I'm sure you guys have learned, you get PV equals nRT. And from here, you can understand, well, what's going to happen if the number of moles goes up? Oh, well, if the number of moles is going to go up, this increases, then volume is going to increase. And so you can understand everything from this just by understanding really how fractions work.
It's all like a working ratio. And all things they're intertwined and and like a relationship, and they all work together.
And that sounds so simple, but it can get really easy, even if you know it, for your working memory to confuse, like, oh yeah, if the volume gets bigger, then the temperature is going to get bigger or smaller. Like, so you just have to take your time to think through that.
Right.
Yeah. And coming back to these basic laws and thinking like in the abstract, not trying to memorize, because if you have this formula, you don't need to memorize. Wait, what happens when the volume gets bigger? Just look at the formula and understand from there.
Right.
So it can prevent you from having to. And as someone like that's big in physics, is like, you don't usually memorize the formulas. You have them, and from there you derive out your principles. And so like sometimes it's the way people think about the rank order of physics and chemistry and biology. When you understand the physics of a system, which you can derive mathematically, then you work out how it's going to play out at the chemical level, and then from there the biology comes from it. Right.
So it seems like you're kind of getting into it now, but like how have like almost like scientists like used that or like manipulated that to actually like benefit humanity in some sort of way? Because like you can even talk about it from like a physicist lens and that kind of thing. You talk about how like even like with like chemistry and how they've used that. So how do you have any examples of that maybe or anything at all?
Yeah. So the ideal gas law is super important in actually a lot of trades. Like that would be one of the first areas of application for sure. Like HVAC, welding. Like you have to understand plumbing to some degree. If you're working with boilers and steam and this kind of stuff. Although steam is really not an ideal gas. It's a very unideal gas. But for ideal gases, it's really important to understand how raising the pressure will affect your volume or your temperature or what the volume. Yeah, go ahead, Bo.
Yeah, I was just going to say, do you want to quickly go into like the term ideal gas compared to why are we talking about ideal gases? What's the business and how do they change when you
So there's a big reason why you only will ever talk about ideal gas in high school because non-ideal gas, the math gets very complicated. So an ideal gas is going to be like your most ideal gases are like your noble gases. So you guys know what noble gases are?
Yes.
Yeah. I don't have to explain that for the purpose of this. Okay. A noble gas, one molecule of a noble gas and one other molecule of a noble gas do not interact with each other very much. There's not a lot of dipole. You guys have done dipoles? Dipole interaction, right? The reason why I said steam is a very unideal gas is like you've got water. Like there's crazy dipole action on the water. So one water molecule and another water molecule are going to have a lot of interactions with each other. So it's a very non-ideal gas. And so ideal gases basically assume that there's really no electromagnetic interaction between one gas molecule and another. That's not true. Like there are no completely ideal gases. Yeah. Because even with a noble gas, there's still London dispersion.
Right.
Yeah, you guys got that. Okay, right. So, and this is one of the cool things where like, I don't know, my background again is more in physics, quantum mechanics, but you guys are farther enough along in chemistry to know that like everything you learn in chemistry is a lie, right? You just get like a better and better.
It's like very gray science.
Yes, here's a carbon atom. It's a nice solid ball. Oh no, wait. There are electrons rotating around. Oh no, actually, and this is where you get when you go further on in quantum mechanics, like it's actually an electron cloud where there's a probability of where those electrons are. And really the only way to actually have a picture of what's actually going on, say in a carbon atom or whatever, is to understand probability distributions. So you really get a picture by understanding the mathematics of it. So when you get there, you realize like, this is where the London dipole dispersions come around. It's like, yes, the probability is that the electrons will be equally dispersed, but at any given time, they're not actually. So you still have interactions between molecules. But the math is close enough. This is close enough that you can treat a lot of gases as ideal. It's like when you pretend that there's no friction or there's no air resistance, right? You have to make these simplifications in order to do some calculations. Especially for things where like the level of precision doesn't have to be exactly perfect. Like you can be a welder and you're estimating the volume you're going to need. Well, the level of precision that you need, you can get close enough knowing what gases you're working with, knowing what the R value is, those sorts of things.
Right. Yeah. Wow.
Because like it's very practical, right? Like how much pressure can you put your gas cylinder under before it's going to become dangerous? Well, that's all PV equals nRT. Right. Or even like if you have an Instant Pot at home, why does an Instant Pot cook faster? Because you've raised the pressure, right? So versus a regular pot, that's the difference between pressure cooking and regular cooking. It's all ideal gas law. Right. So you can cook faster in a different, and there's some other reasons too, like you keep the water in, but that's a different situation. But the pressure it changes how you cook. Or like if you lived in like Tahoe, like we're really close to sea level, right? Yeah. If you've ever even seen in recipes online, a good recipe will like, if you're at high altitude, you need to change the temperature and the cook time, because the pressure difference between where we are in like say Lake Tahoe is enough to change the interaction of the volume and the temperature together.
Really?
Super interesting. Thanks for some of the practical applications. I think we might take a turn here for one of our last topics. We want to talk a bit about the atmosphere and some of the challenges that we face. So just changing topics a bit, do you think that current technologies are actually enough to reverse some of maybe the atmospheric damage, or do we need entirely new situations and solutions, or how can we sort of pivot towards, you hear all this ordeal about a climate crisis, or our atmosphere is in trouble, or the ozone, there's holes in the ozone, right? So do we actually possess the technologies to start to reverse these things, or I don't know, what's the deal? Can you maybe touch a bit on that?
I don't know.
Yeah.
So what I will say is, when I was younger than you guys, we weren't so much talking about climate change or global warming, but the ozone layer was a big, like we heard a lot about the hole in the ozone when I was in elementary school or something. And I know there has been some good over the last 20, 30 years that the hole in the ozone has, depending on what word you want to use, repaired, gotten smaller. There's some change in that we've been able to document as we've paid attention to that. Now that's a related but different issue from carbon emissions and global climate change. It's related, of course, but there is a different issue there. But I guess maybe the only value I could add to this question is to say, like, we said no gases are ideal, and this is the ideal gas law. And now, like, just multiply that millions of times by the level of complexity when we get to atmospheric chemistry. Like, it's good to understand some of these basic things, but I think it's a really complex question that I'm glad that there's lots and lots of people thinking about and lots of people researching, because we need that, and we need somebody who's an expert in this one thing and somebody who's expert in this one thing, and then putting that data together. I think when it comes down to the individual person, and maybe this is where I'll put my other profession hat on. As a Christian, I believe that, like, right in the first pages of the Bible, God creates humans and is like, hey, have a bunch of babies and rule the earth, take care of it, subdue it. So, like, as a Christian, I believe it's my responsibility to care for creation around me. And in the position that I'm in, I am not in a position to make global policies or national policies. I am in the position to vote. So I should educate myself enough to vote in a way that it at least takes into account how I think our government plays into taking care of God's creation. But the main way that I, as like an individual human, can actually deal with these things are some of like the really, really practical stuff. Like, there are things we know are good and not wasteful. Like, my husband was in mining for 15 years. I'm really passionate about recycling aluminum, because, like, the amount of work and energy and money and some environmental damage, although we're a lot better in Canada about mining in responsible ways than in a lot of other parts of the world now than we were 100 years ago. But, like, it takes a lot of work and it costs the earth a lot to mine out aluminum, and aluminum is infinitely recyclable. Like, it's really, really worth the effort for you to go and keep your pop can and recycle it in a place that actually recycles aluminum. Plastic, that's another issue. And so you hear a lot about what's going on, like, that maybe our plastic recycling isn't all actually getting recycled and maybe it's just getting burned. And that might be true, but, like, it would be foolish for people to be skeptical of all recycling because of what's going on with plastics. Like, aluminum is infinitely recyclable. And paper, we have Abitibi, we have places right here in Niagara that recycle paper that actually gets used. So I think the small choices that we actually, like, or young people actually have control over is, like, am I just going to toss this pop can, or I'm going to wait and actually make sure it gets in an actual recycling can? These are things that you can actually do that make a difference. Because when you go to, like, aluminum, the amount of water, fresh water that's used to refine aluminum, the amount of energy and carbon emissions and all kinds of gases that whatever effect they have. So I think those small doable things. And then I would say, I guess the one other thing for people your age is, if you're really passionate about it, like, what do you want to go on and study, and what little part do you want to get into? There's a lot of opportunities for young people, even doing their undergraduate degrees, to do research. One summer after 4th year, I got a research grant, and I was able to do, not at all in this area, so I won't tell you what it was about, but I got to work with a really cool microscope. But there's lots of opportunities to try that and see, like, do I actually want to go into academia and research, and is this something I'm passionate about that I want to dig into and find answers to?
Yeah.
So I don't know if any of that's valuable to you.
No,
but
no, I think that's really cool, because I think that's a very applicable piece. And as like Bo and I, as just like students, are just curious to actually understand the natural world and how we can make our footprint and actually like inspire change and do these different things. I think that's actually like a very applicable piece, and I think it's really cool to see how passionate you are from your experiences and from your husband's experiences to see how this affects our world and how something needs to change, and just to see also how encouraging it is that some things are changing.
Yeah, that's right.
But there's still a lot more that needs to be done.
And so, maybe one thing I'd add to that might be more controversial, but I am really passionate about nuclear power. As a physicist, obviously, like a lot of, I think there's been a lot of, it's easy to be afraid of things because of a few incidents that really stick in your mind, but the number of cancer deaths by coal power is like, I should have looked up the stat before, but we're talking about hundreds of thousand times more people have gotten cancer because of coal power than the few hundreds that have happened because of 3 Mile Island or Fukushima. Right. I don't even think they've been studying the Fukushima fallout, and there's minimal. Nuclear power, especially fission, it is maybe not the answer in all countries and political climates, but we are getting close to fusion, which, like cold fusion, we can do fusion. Cold fusion means that you get more energy out than you put in to do fusion. And like the product of fusion is helium. There is no radioactive fallout. And so we're continuing to make strides there. And I think definitely in my lifetime, and I think definitely in your lifetime, we're going to see fusion power. And that is huge, because like wind and solar have their applications, but they probably can't provide enough power to bring the entire, the entire developing world out of developing into developed. As countries develop, they need more energy. And so if we want to lift up people out of poverty, then we need a lot of electricity that's clean electricity. And so I think those are really important. And when it comes to also the atmosphere and other things, but there's just so much that comes out of having clean power, especially clean in like not giving people cancer, clean as in for the atmosphere. And so nuclear power, I would just really encourage people, if you're afraid of nuclear power, there's a lot of good research out there, and find more out about fission and fusion. And take grade 12 physics and learn about fission and fusion.
That is cool. That's cool to see things like when we discover about the natural world, like stuff like this actually being applied into helping people indirectly. I mean, that's what kind of science and the medical world is all about. So that is cool and encouraging.
Yeah, and I can kind of say like that as someone who like watched the Chernobyl series and that kind of thing, I was automatically a little more leery about it. Hearing especially about like some of the plans that Canada has, and making these nuclear power plants and all these different things. But it's really encouraging and cool to hear that. And I have so many questions, but I don't think we have enough time to get into all
and that's a little outside of the scope of the ideal gas law.
Conversation for another time.
Yes,
the next episode on the
on the podcast. I think Bowen has one more question that he'd like to ask, and that's
just finishing up here. We know you have a teaching background, so you might appreciate this one. Is what do you think is the most misunderstood concept students have about either climate science, atmospheric chemistry, or maybe gas laws?
To go directly to the ideal gas law, like I said, you don't have a really intuitive understanding of how fractions work, literally. So then this becomes confusing to you. But in terms of the bigger picture of climate science, all this kind of stuff, I think you hear one thing and it tends to be like, oh, it's got to be this way. And remembering that those things are incredibly complex. Or like, again, it's off topic, but you took up of course, you're going to watch Chernobyl. Great. is serious, by the way, and be like, nuclear power, this is insane. But there's a huge complex web of how these things are all interconnected with what are the risks that we take in certain areas and what are the cost benefit analysis. So I guess to say, like, I think everything has its place. Like, there are places like rural Canada, until we have small scale nuclear reactors that are semi-portable, like the best fuel that they can use is fossil fuels. So can we save the fossil fuels for remote areas and places when you need to run off of fuel?
Yeah.
And can we transition places that don't need that into cleaner sources of power? And so it's like, I guess a lot of things aren't all or nothing. Everything's a trade-off. There's a trade-off to economic development, and economic development is important because it's the lives of humans. Like, economic development, I don't mean about like rich people making more money. I mean like the everyday person who's living off of $2 a day. If we can set up a system where they can start making $4 a day, like, this is huge. Right. And I would say the other biggest thing is people really have a catastrophic view. If you've never been on the website Gapminder, super encourage it. Like, if you ask most people, in the last 30 years, has the number of poor people doubled, gone in half, or stayed the same? What would you guys say? Like, poor as in living on less than $2 a day.
Less than $2 has it
doubled?
Well,
stayed the same, or halved?
For the sake of this, I would think that you're getting at it doubled. But
I was gonna say
it's halved. Like, it's more that the number.
I thought you were gonna say it's like increased because
no, it's way better.
Okay,
way better.
Okay.
What has happened in the last 30 years to bring the world's poorest out of like under $2 a day poverty is amazing, really? And most people don't know that. You ask them, they think everything's gotten worse, and that's not reality. Like, some things have gotten worse, but on the whole, way fewer people, like less kids are starving to death. Less kids under 5 are dying. Like, we've made huge strides in those areas. So maybe, sure, I've talked too much and you're gonna have to cut out stuff. If you ask me, like, what's the most misunderstood thing? It's that everything's getting worse. We're all doomed. Gen Z is basically gonna die. They can't, Gen Alpha's, never gonna be able to afford a house, everything. Why would we even have kids? Because everything's gotten worse. Like, look at actually all the data. The poor who are being lifted out of poverty, the infant mortality rate that's gone down, the literacy rate among young girls that has skyrocketed in the last 30 years. Like, you can't just look at the catastrophe. You need to look at all the data. And the wider picture is that there's a lot of really amazing things happening that are being moved forward. And even in the area of like climate science, atmospheric change, how we're generating our power, there's a lot of hope. And so I think it would be really important, especially for young people, to know that as well, and to look into that, and then be part of, like, how can we be part of moving things forward?
No, that's first of all, that's very encouraging for me, because like, even like when you asked that question, I said doubled.
Yes.
And so I think clearly I'm an example of a narrative that's been constantly being spread throughout our society, that like things are exponentially decaying.
Yes, and that's right. That's right.
As we learned in math.
Yes, very good.
So, hearing that's actually really, really encouraging, and seeing how also, like, scientists almost walk this sort of tightrope in a way of economic success, but also at the same time not harming the future generations and being sustainable.
That's right.
And so that's really cool and really encouraging.
And a lot of times we have that narrative that the economic success versus environmental sustainability are against each other.
Yeah.
But a lot of times that's not actually true. You can give people clean power that also lifts them out of poverty. Yeah. Like, if you want to prevent cancer in young mothers, you get them to stop cooking over stovetops, like open fire stoves that causes huge amounts of cancer. We give them clean power where they can cook over something that's not giving them cancer. Like, this is win-win. And it takes them less time, so they can be more productive and make more money for their families. Right. So a lot of those times, like, those things aren't in contrast with each other. And I think what you've expressed too is sometimes we can get a very North American view. Yeah. So have gas prices gone up huge? Absolutely, because of things that are going on in the world right now? Absolutely. Yeah. Is it harder for you to own and buy a home than it was for me as a millennial, or certainly boomers, yeah, absolutely. But like, we're only part of the world, and there's a lot of people living in a lot of other places of the world, and because and that's why it's encouraging to to look at what's happening across the globe for people.
Yeah, I think you
have a lot more content than anyone's ever going to want to watch. Yeah, hack and slash.
Yeah, we really appreciate your time and just your school and your expertise. So I think that is a wrap.
Yeah, that's great. No, hack and slash that, boys.
Sarah. Yeah.
Hopefully you'll get 5 good minutes out of that.
No, I think I don't even know where to cut. Honestly, that was all incredible.
We can talk about